Hi everyone. Today I will present our work, Trust Regions for Explanations via Black Box Probabilistic Certification. And this is joint work with Swagatam Haldar, Dennis V. and Karthikeyan Ramamurthy. And I'm Amit Dhurandhar. So just some brief background about explainable AI. So explainable AI is about providing explanations for models' decisions. So for example, a model may predict, say in the Helloc dataset, that someone's profile is bad or they shouldn't be essentially given a home equity line of credit loan. And so someone might ask why, and methods such as, say, for example, Lime might provide an explanation as seen here, where they might say it's because the average months on file or the most recent sort of inquiries to the account were a lot, and so on and so forth. And they might give a certain form of explanation, while SHAP also might give a similar kind of explanation. And you can always measure the quality of the explanation in terms of, say, a popular metric is fidelity, where you essentially compare the output of the, say, Lime model to the actual black box's prediction, and you see how close it is. And you can, the closer it is, the better. So higher the fidelity, or closer in this case it is to 1, the better it is. The closer it is to 0, the worse it is. And so what you have here is essentially like x0 is the instance, which has obviously, values for different features. Then ex0 is the explanation, which could be, say, for example, in this case, like a Lime explanation, which is feature based, or also a SHAP explanation, which is feature based. And then you can compute, like, once the explanation is there, quality metrics such as fidelity in this case. So the problem statement that we have is that given a black box model, a prediction for an input and an explanation for an input, can you and a quality measure such as fidelity, like I just showed, or but it could be anything else, such as even stability or some other metric. Essentially, can we find the largest region around the input where this explanation is still valid? That is, the explanation meets a certain quality criteria, such as, say, for example, the fidelity being greater than some amount. So this is like the more formal definition. So what we are searching for is, say, given a predictive model G and an instance x0 and also an explanation function and a threshold theta, can we find basically a region around x naught such that the fidelity or whatever the quality metric is will always be greater than theta. And I will sort of interchangeably use the term fidelity and quality metric here. Please note that you could use any quality metric that you deem appropriate, and our method should sort of should seamlessly apply. So this is the general flow. So you have a black box model, you have an instance, and then you also have some explanation method and a quality metric. And what we are searching for is, given this x0, can I find like the green box here, a certified region around this x0, so that for all inputs around in this certified box, the explanation will satisfy a certain threshold for the fidelity function or quality metric. And why, like, what's the point of this? So the point is this, that there are multiple sort of uses of this. So explanations generally are local to an input, and what this will give you is some kind of guarantee of the model's behavior around that input, because it will say that the explanation will have certain quality around the input, and which is generally measured with respect to the black box's behavior. Then stability of explanations is another sort of use, is that it'll also tell you how stable certain explanations are, and how sort of like valid these explanations are. And this is useful for recourse and many other things. So there are works which show that stability is important for many kinds of stakeholders in different applications. So this is one way of sort of ascertaining stability. Then often explanations are too costly to compute, especially in the black box setting. So for example, like Lime and all take a lot of query calls, usually like thousands, to get a single explanation. But if you're able to find a region, then you can essentially save a lot on the number of queries you might need to get explanations for a bunch of inputs, because once you have that region, you can essentially use that same explanation for multiple points, and so you don't have to recompute explanations for each of these points. And We'll see in some of the experiments later that using our method, you can get huge query savings. And last but not the least, you can also use this as a metric to compare, sort of a meta metric to compare explanation methods. As you can see, like the size of the certification regions for different explanation methods. And so if the region sizes are larger for a certain explanation method, it might mean that it is providing more sort of generalizable explanations. In terms of prior art, we believe this is a new problem, and it's been sort of stated for the first time. And so there are no sort of direct competitors for our approach that are there in literature. I mean, there are a bunch of obviously explainability methods, and there are different types of explanation methods also, such as things like sufficient reasons, pertinent positives, and even if explanations, but they don't exactly fall in this category. And the important point here is that most of these things are like most of these explanation method types are for feature-based explanations, but the proposal we have here could be applied to any kind of explanation. So they could be exemplar-based explanations or anything else. The methods that I will describe shortly will be applicable, as all you need is basically something to measure fidelity of the explanations at different points. The closest thing in terms of methods is probably things from adversarial robustness, where they try to find sort of certification regions or try to find essentially how robustness of certain classifiers. But those are sort of special cases of but those are essentially special cases of the problem that we have here, where the explanation function can be thought of as a constant. Also, like many of the works there, either are white box or work on smoothed versions of the black box, while we do not require any of these assumptions. We work directly with the black box that's given to us. So this is essentially one part of the method, which is the broader strategy, which calls a certain function called certify, which basically certifies a region. So the idea of this particular function, which calls certify, is that it'll basically choose a region to certify. And if this certify thing returns a true value, then it will search for a larger region. And essentially, it will try to double the region size. And whenever it hits a point where it finds invalid inputs, that is where the explanation is not that good, then it will sort of try to do a sort of a kind of a binary search between that point and the previously certified regions. And so it will try to essentially find the largest region around the point where the explanation will have a certain quality guarantee or a certification set. And these are, but so like I said, so it calls this function certify. So the question is, how does it certify? And so for that, we provide three alternatives. So one is uniform sampling. I mean, this is the simplest, but since, like I said, this is, we believe to be the first work in this area, we wanted to provide something that's simple. But as you'll see later, this doesn't necessarily work very well in very high dimensions. So we propose two other methods. One is called uniform incremental, which basically samples certain prototypical examples randomly in the space and then samples around these using Gaussians. And you essentially, what you do is you sample more and more of these prototypes, and then you sample using Gaussians around these prototypes, but maintaining a certain sort of query budget. So the more prototypes you have, the less points you'll sample around it, and vice versa. And the last one, which is the most interesting method, and which we have found to be very useful in high dimensions and scalable, is an adaptive method, which basically again samples prototypes. But then once you sample points around these prototypes that you check for validity, the prototypes around which you find things that have the lowest fidelity, you start sampling more around those points. So it's kind of like an adaptive method which does sort of an adaptive grid search, while the uniform method could be thought of as doing like a random grid search or random or sort of non-uniform grid search. So these are three methods. So we can look at them a little more closely based on simple examples. So let's just consider a simple 2D example where you just have a linear function of two variables, and an exponential function is also linear with a different slope, and say the theta, like the quality guarantee that you want on fidelity, is 0.75. And so what you see here in the left is you basically like level sets of this fidelity function. So what you want is basically a box around the start that is the point you want to certify probabilistically, where you get a box that, where all the points within it will have a fidelity of at least 0.75. And so given these level sets, it should lie within it. So if you look at the uniform strategy, what it does is, like I said, you start with a certain random size for the certification region, and you sample in this case like uniformly in that region, and you'll find like the green dots are where the explanation fidelity thing is valid, while the crosses are where the fidelity is lower. So you might find like essentially like points where it's valid, and then you might find a point where it gets violated. So once you find that, you know that that region is not the right region, so you go down to a smaller region, usually half the size, or between, now in this case, like yes, half between the point and the previous size. And now in this case you find that like, okay, like everything is valid. So now you know that this region is definitely certified, but you want the largest region. So you take between that region, that is the one that's certified, and the one where you just found the like the violator, and then you again sample within this sort of ring, again using uniform sampling, and you might find some points that are violating the fidelity constraint. So then you again become like choose a smaller region, and so on and so forth. So you can keep on continuing until like a certain number of iterations are met or a certain convergence criteria is met, and then this is your final sort of certification region. So this is the uniform strategy. Now in Unify, like I said, you don't sample this uniformly. You sample like prototypes, and then around these prototypes, you sample points using Gaussians, and then you query those, and you keep on doing that. You again sample more prototypes and more prototypes, but then fewer and fewer samples around these, and this continues. So like I said, it's like a dynamic grid search, and then once you certify, you again do the same thing. You double the size of the region. Now you find in that ring region, if you find certain violating thing, you again half the region size, and this keeps on going. So until like I said, until some convergence or iteration limit is met. And so this is like basically like like a dynamic grid search kind of strategy, and it's still non-adaptive, as you just randomly sample. And now the last is the adapt strategy, where so say you have some points you sample, now here, like you see, you sample around these, then you sample again, like when you're more prototype, you sample fewer, but then you find that, for example, like these two had lower fidelity points around them, so you sample more around these points now. So it adapts to the prototypes that are closer to violating examples. Now and then the process continues. So you again sample more. You again see, like, so for example, these 4 prototypes that you sample something, but you find that around the corners there are more low fidelity examples. So you sample more around there, because there you're sort of, the intuition is you're more likely to find the violating examples. And so this like this process continues of sampling more and more prototypes, and then just focusing on ones that are more promising in terms of finding the violator. And again, you sample in these regions, and yeah, this basically this process continues. And so as you can see, this is like a adaptive strategy, as it adapts to the fidelity of the points where it samples. And yeah, so this goes on, and eventually you get your region which is the certification. So these are the 3 strategies. So we also have theory around this. We have like finite sample bounds on the quality of these regions, and the nice thing is that they are exponentially decaying bounds with the number of queries. So it means that, especially for like the adapti strategy, and even unified to some degree, like even with like a smaller query budget, you could get like with very high probability, like accurate certification regions. More so, like if you see, like our bounds do not depend directly on dimensionality, but it depends on how sort of uniform the fidelity distribution is. So because the dependence on dimensionality is not explicit, you could have like even high dimensional data, but if the functions are not too complicated, these things will converge fast, which is nice to have. And since like adapter, like I said, samples more around promising prototypes, also in practice we see that it works well, especially in very high dimensions. Then besides that, we also have in the paper like some CDF free bounds And also, if we assume more things about the black box functions, such as Lipschitz-Nets or piecewise linear, then what sort of additional improvements or advantages you could get. So now let's look at some experiments. So we assume that the fidelity threshold is 0.75. In the synthetic experiments, we use a piecewise linear function. In the real experiments, we have experiments on tabular and image data sets where we go from low to high dimensions. In the baseline, like I said, like this is the first work in this direction. So we adapt a zeroth order optimization attack method from adversarial robustness for our problem. Now, these are some synthetic results. There are a lot of numbers here, but I think the thing to see is like the rows, the D is basically the dimension of the data, and the optimal W, which is the width of the box, right? The certification region is 1 by D. So when D is 1, the optimal width is 1. So you can see all the methods recover 1. When it's 10, it's 1 by 10, which is 0.1. So you see that as as you get more and more queries, which is Q, these methods converge and so on and so forth. But I think the interesting thing to see here is that essentially, like for low dimensions, UNIF works pretty well. Unify works well for medium dimensions, like like around hundreds to thousands, while Adaptai is very good in 10,000s. And especially like you see the speed, the time, that is time it takes to find. Our methods are at least 1 to 2 orders of magnitude faster than ZO plus, which is the adapted adversarial robustness method from one of the toolkits, which is sort of touted for being efficient. So even using an efficient adapted adversarial robustness method, our methods are significantly faster, like up to like 2 orders of magnitude faster sometimes. So, and this is from real data set. So this is using ImageNet data set, which is like 40 around the order of 40,000 dimensions. And you can see that what you see here is like, of course, we don't know the actual certification widths right here because this is a real data set. But if you look at the left plot where we have a Lime explanation, you can see that as the x-axis, which is the number of queries, increases, the method sort of converge to the similar point. So you can assume that that is probably the right certification region, where the y-axis is the width. But the interesting thing is, so all of them converge to roughly the same value, like which includes the ZO plus. But as you can see on the right, the second plot, our methods are significantly faster in this case as well. Like ZO plus is much slower. And then as you can see later on also in the right two plots, which is for SHAP, you see a similar behavior. And you can see also like many times even our methods converge faster. So, and then there's some interesting insights here. So for example, right, like you can see here that if you look at the Lime, the first two plots, which are Lime in like the left two and the right two are SHAP. On the top row, you see that you get higher widths for a certain fidelity threshold, right? Like so, Lime explanations in this case were more generalizable around that point. But in certain cases, like you can see below, like even for the point in question, the fidelity was lower than the threshold set, so you couldn't find anything. So there are trade-offs. So these kinds of trade-offs and all become more explicit using a method like ours. And like I had promised before, we also have a query savings experiment. So what you see here in the left plot is the x-axis is the number of points that are covered in the training set, and the y-axis is the number of points that for which we found the certification regions. And as you can see, like the y-axis on the right is basically percentage savings in query. So if I were to find like explanations for each of those points, how much do I save by finding these regions? And you can see that we can save up to 80% of the queries that are there. And the right plot just shows that like the regions we find with very high probability, the certification criteria is met, which is here is like the threshold being over 0.75. So that sort of validates that. Then we also do an experiment looking at stability of explanations, and we see that explanations within a region are much more stable than those outside. So the top table shows sort of quantitatively how good these explanations are. And you can see that they're statistically significantly more similar within our regions than if you take something outside the region. And below you can see in the radar plot, essentially each of the radar points, like these F things, are essentially feature values, and the black thing is the explanation of the actual point. And you can see like the green, which are explanations within the box, are much closer to this than the red, which are explanations for points that are chosen outside. And so in summary, basically, we have provided a formalization for a new problem of explanation certification, which is novel to the best of our knowledge. The probabilistic certification, yeah, like I said, is not just limited to feature-based methods, but you could use this for almost any method where you can essentially have a fidelity metric and where you can apply the explanation to different points. Then we have exponentially decaying finite sample bounds, which, like I said, only implicitly depend on dimensionality. The methods, especially like the adaptive method that we have, is highly scalable and efficient, and our code is going to be available at on our AIX 360 explainability toolkit. So for all of you to try out. So with this, thank you, and thanks a lot.